Okay, particle motion is just literally an update on the particle motion stuff that you already have. So recall in particle motion problems, you have two cases. One case is a one-dimensional case where you have a bead on a string that's moving back and forth. And we usually use x sub t to give you the position of that bead. So if you recall, we know that x of t is the position, like we just said. And if I take x at t2 and I subtract x at t1, this is an indication of displacement. Okay. X prime of t, sometimes called v of t, is the velocity at time t. So this is the displacement from t1 to t2, right? So this is the velocity at time t. If I take the absolute value of the velocity, I get the speed at t. And finally, if I take the double derivative of t, this gives me the acceleration at time t, or the derivative of the velocity, and that's the acceleration at t. Okay, so we're going to add a couple things to this. So this is your new information. If I take the integral from t1 to t2 of the acceleration, then I get back the velocity at t2 minus the velocity at t1. Likewise, if I take the integral from t1 to t2 of the velocity at dt, I get the position at t2 minus the position at t1. So these just follow along from what we have above with respect to the fundamental theorem of calculus. And if I take the integral from t1 to t2 of the absolute value of the velocity of t dt, this is going to give me the total distance traveled from t1 to t2. So the absolute value in there is going to give me not just displacement, but it's going to add up the distance that I've traveled all along. So this is probably going to get broken into multiple integrals depending on the sign of the velocity at different intervals between t1 and t2. So really all we're doing here is we're taking this initial idea and we're adding and amending this so that we can throw in the fundamental theorem of calculus pieces and then work out how to deal with total distance traveled and not just displacement. So it's important to note that these two things are calculated differently. Here you can work from the position vectors. So literally, if you take the integral of the velocity, you get the displacement. But if you take the integral of the absolute value of the velocity, you get the total distance traveled. Okay, so that there is the first dimensional case. Now let's look at the two-dimensional case. Okay, so some recalling of the drawing for the two-dimensional case here. You have like a curve, a space curve that starts at time t1 and goes to time t2. And we use a vector valued equation where you have an x of t and a y of t to describe that space curve. Okay, so note that vector valued function, right, the x of t, y of t, is the position vector for the particle at time t. If I take the derivative of that, right, I get x prime of t, y prime of t, and if we recall that that was the velocity vector, right? So if I take the magnitude of the velocity vector, right, which is square root of x prime t squared plus y prime t squared, that's the speed of the particle, right, at time t. And again, the second derivative of the position vector, which is going to give me x double prime of t, y double prime of t, is the acceleration of the particle. Okay, so again, we have things to add in here, right? So we're going to add some new stuff. If I take the integral from t1 to t2 of the second derivative, or so it's the acceleration vector, I'm going to get back the velocity vector at time t2 minus the velocity vector at time t1. So again, this is just banking off the fundamental theorem of calculus. If I go from time t1 to time t2 of the velocity vector, I get back the position vector at t2 minus the position vector at t1. So this is a displacement vector, right? So that's a vector that describes the displacement of the of the particle. So likewise, just like in the first case, instead of taking an absolute value here, I'm taking a what's it called? The magnitude. So if I take the integral of the magnitude, right? So another way of writing this is t1 to t2 of the square root of x prime t squared plus y prime t squared. So I'm literally, if you recall, this is the speed, right? If I take the integral of the speed, this is total distance traveled by the particle from time t1 to time t2. All right, so that's really all the information that you need to deal with particle motion problems. We will get into arc length in the next section. But that's what we need for this section, and we kind of move on. So there you go.